nuggets of knowledge to shortcut you to being well-informed. Today, we're diving deep into something you interact with literally every single day, but likely never truly think about. Photon polarization. We're going to unpack how light's subtle orientation dictates everything from, that annoying glare off a lake,
Right.
to the kind of ironclad security of quantum communication, and maybe even the very nature of reality itself. It's quite a journey.
It really is. And what's fascinating, I think, is how this concept, which really started with simple observations about classical waves, has evolved. It's become a cornerstone of quantum mechanics, and now it's driving all this next-generation technology. We'll try to guide you through that journey from the basic physics to some really astonishing applications.
Okay, so before we get into the, let's say, quantum oddities,
Yeah.
let's ground ourselves. For a long time, light was just seen as a wave, right?
Exactly.
So in that classical picture, what is polarization? What's it telling us about how light behaves?
Well, polarization is intrinsically linked to light being a transverse electromagnetic wave. So imagine like a jump rope.
Oh.
You flick it up and down, the wave travels horizontally. That up and down motion is perpendicular to the direction the wave's moving. Light's electric and magnetic fields oscillate perpendicular to each other, and crucially, also perpendicular to the direction the light's actually traveling. Polarization is specifically about the geometric orientation of that electric field's oscillation.
Ah, okay. So that makes it different from, say, sound.
Totally different. Sound waves are longitudinal. They oscillate along the direction of travel. So polarization isn't really a relevant concept for them. And most natural light, from the sun or just a regular incandescent bulb, it's unpolarized, meaning its electric field is vibrating sort of randomly in all possible directions perpendicular to travel. But when light becomes polarized, those vibrations are restricted to a specific pattern.
Okay, a specific pattern. So what are the main types, these fundamental types of polarization?
We usually break it down into three fundamental types, and it's defined by the path the tip of that electric field vector traces over one wave cycle. The simplest is linear polarization. Here, the electric field just oscillates back and forth along a single fixed line, straight up and down, or side to side, basically.
Got it. Simple one.
Then you have circular polarization. Now imagine the tip of that electric field vector isn't just moving along a line, but it's rotating in a perfect circle, keeping a constant strength as it goes. This happens when you have two perpendicular components of the field that have equal strength, but they're perfectly out of sync by exactly 90 degrees phase difference.
Out of sync. Okay.
And we even talk about handedness here. Circularly polarized, or RHCP, rotates counterclockwise as you look at the wave coming towards you. Left circularly polarized, LHCP, rotates clockwise.
Handedness, right.
And finally, the most general state, and actually the most common one, is elliptical polarization. Here, the tip of the electric field traces out an ellipse. This usually happens when the perpendicular components have unequal strengths, or maybe their phase difference isn't exactly 90 degrees or 0.
So most light is actually elliptically polarized if it is polarized.
If it's fully polarized but not perfectly linear or circular, yeah. It's worth noting, though, that linear and circular are really just special cases of elliptical. Think of an ellipse squashed completely flat into a line, or one where the major and minor axes are equal, making it a circle. They're sort of degenerate cases.
That makes sense. And you mentioned light can be a superposition of components, even in this classical way of thinking. So how do we actually picture these states? Is there a good way to visualize them?
That's a great question. How do we make this concrete? A really powerful visual tool is the polarization ellipse. Just imagine drawing the path that the tip of the electric field vector traces in a plane, perpendicular to the way the light's moving.
Like watching the end of that jump rope.
Kind of, yeah. Sometimes it's a line, sometimes a perfect circle, but most often it's an ellipse. The polarization ellipse captures that shape. It tells us its shape, its tilt angle, whether it's spinning clockwise or counterclockwise. It's like a visual fingerprint for the polarization state.
Okay.
And this geometric picture, it provides a really nice link between the abstract math and what we can actually observe. It also sets us up nicely for something called the Poincare sphere, which we might get into later.
Right. So for centuries, this waves model worked beautifully. But then things started to get weird, didn't they? Like with the photoelectric effect.
Exactly. That was a big one.
This is where it gets really interesting, I think. How did polarization go from being just a wave property to something we attribute to individual particles of light?
You're absolutely right. The classical wave model hit a wall. Things like the photoelectric effect, where light only kicked electrons off metal if its frequency was high enough, not just its intensity, just couldn't be explained classically. This led to Einstein's, well, revolutionary idea that light itself is quantized. It comes in discrete packets of energy we now call photons.
The photon.
Yeah. And the huge question then became, okay, if light is particles, how does polarization, this wave property, fit in? Does it even make sense? And amazingly, experiments confirm that yes, polarization applies to each individual photon. That was really the start of the whole quantum mechanical view of light.
That's a massive conceptual jump from a continuous wave dimming smoothly to individual photons. So Malice's law, classically, it describes this continuous dimming as light goes through a polarizer. How do we rethink that for a single indivisible photon? It can't get dimmer, can it?
It can't. That's the core of the quantum reinterpretation. Classically, Malice's law says intensity drops off as cosine squared of the angle between the light's polarization and the polarizer's axis. Smooth dimming. Quantum mechanically, a single photon is all or nothing. It either gets through the filter entirely or it's absorbed. It doesn't get partially through.
So what happens to the cosine squared?
It becomes the probability that a single photon will be transmitted.
Wow. Probability.
Yeah. And sine squared of the angle becomes the probability that it gets absorbed. So for each photon hitting the filter, it's like a quantum coin flip weighted by that angle.
That's fundamentally different.
It's a complete shift. From deterministic dimming to probabilistic transmission, it preserves the photon's identity as an indivisible particle. And if you think about the bigger picture, the polarized photon becomes this amazing synthesis, right? It unifies the wave and particle views. It acts like a particle when detected. Exactly. But it carries this wave-like property, its polarization, that governs how it interacts statistically.
Okay, this idea of probability instead of certainty, that's mind-blowing. And it leads us straight into the heart of quantum mechanics, this idea of a qubit. How does photon polarization become a qubit?
It's actually a perfect physical example of a two-level quantum system, which is what we mean by a qubit. Just like a classical bit is 0 or 1, a qubit can be 0 or 1, or crucially, a combination of both at the same time. And any polarization state can be described as a combination of just two fundamental orthogonal basis states.
Orthogonal meaning completely distinct, like perpendicular.
Exactly. Think of common pairs, horizontal and vertical polarization. That's the rectilinear basis. We often write them as Urnia and V in quantum notation, or you could use the diagonal basis, plus 45 degrees and negative 45 degrees, maybe E or Eos. Or the circular basis, right and left circular, Ario and Uriola. The key thing is, any polarization state you can imagine, say, R, can be written as a linear combination, a superposition of just two basis states, like Oreo plus Aureo.
And those alpha and beta things.
Those are complex numbers called probability amplitudes. Squaring them tells you the probability of finding the photon in the S state or the DVA state if you measure it in that basis.
Okay, let's unpack this concept of superposition, because it sounds completely bizarre from our everyday experience. What does it really mean for one photon to be in two states at once?
It is bizarre. Superposition means the photon genuinely exists as this combination of states simultaneously. It's not like it's rapidly flipping between them or that we just don't know which one it is.
Not just hidden information.
No, not hidden information. It's fundamentally in both states. For example, a diagonally polarized photon, B, is a coherent superposition of horizontal and vertical, D8+. This literally means if you set up a detector to measure horizontal or vertical polarization, there's a 50% chance you'll detect it as horizontal and a 50% chance you'll detect it as vertical. Before the measurement, it was genuinely both.
And this depends on how you look at it.
Absolutely. The description as a superposition is relative to your chosen measurement basis. A photon that's definitely horizontal-ish is actually a superposition if you decide to measure it in the diagonal basis or the circular basis. It's all relative.
So if a photon is in this superposition state, just chilling out, being both H and V, what happens when we actually measure its polarization? You mentioned wave function collapse. That sounds pretty dramatic.
It is dramatic, and it's maybe the weirdest part of quantum mechanics, the measurement postulate. See, in classical physics, measuring something just reveals a property that was already there.
Like measuring the length of a table.
Exactly. But in quantum mechanics, the act of measurement seems to actively force the system to choose a state. It participates in defining reality. When our photon in superposition, say our diagonal one, hits a measuring device, like a vertical polarizing filter, its state changes instantly. Discontinuously, that's the collapse. It jumps from being a superposition, part H, part V, into one of the definite states allowed by the measuring device. So hitting a vertical polarizer forces it to become either purely vertical and pass through, or purely horizontal and get absorbed.
And the chances of each outcome
Are determined by those squared amplitudes in the original superposition. For our diagonal photon hitting a vertical filter, it's 50-50. And here's the kicker. The state is irreversibly changed. If that diagonal photon passes the vertical filter, it emerges as a purely vertical photon and has completely lost its memory of ever being diagonal.
It forgot it was diagonal.
In a sense, yes. The measurement destroyed the original superposition, and this very property, this irreversible change upon measurement, is fundamental to how quantum cryptography works.
Okay, that is seriously counterintuitive compared to just dimming light. Is there a simple experiment that really hammers home this difference? Something that shows this isn't just a classical mixture we don't know about?
Oh, absolutely. The classic demonstration is the Three-Polarizer experiment. It's beautifully simple and profoundly weird. Okay, set up two polarizers with their axes crossed, say the first one vertical and the second one horizontal.
Right, so vertical light hits a horizontal filter, nothing gets through. Makes sense.
Exactly. Classically and quantum mechanically, zero light passes the second filter. Now here's the magic trick. You take a third polarizer oriented diagonally at 45 degrees, and you slide it in between the first two crossed ones.
Wait, so vertical, then diagonal, then horizontal. Adding another filter should block more light, shouldn't it?
Classically, yes. It should only ever reduce the light or keep it at zero. But quantum mechanically, light gets through the final horizontal polarizer now. It's sequential wave function collapse. Let's trace a photon. 1. Unpolarized light hits the first vertical polarizer. Photons emerge vertically polarized in the view. 2. These RV photons now hit the middle, diagonal 45 degrees polarizer. But remember, RV is a superposition in the diagonal basis. It's half RD plus 45 degrees and half RE minus 45 degrees. So about 50% of the photons collapse into the area state and pass through the diagonal filter. The other 50% collapse to AA and are absorbed. 3. Now, these purely diagonal air photons hit the final horizontal polarizer. But AJ is also a superposition in the HV basis. It's half air and half EA.
So it collapses again.
Right. 50% of the area photons collapse to area and pass through the final horizontal filter. The other 50% collapse to AA and are blocked. So overall, starting with unpolarized light, you get 12 through the first filter, 12 of those through the second, and 12 of those through the third. Net transmission is 18th.
Wow. So putting the middle filter in actually allows light to pass where before there was none.
Precisely.
Right.
And there's no classical explanation for that. It's a direct consequence of quantum superposition and measurement collapse. It proves superposition is real and fundamentally different from just a classical mix.
Okay, that's a fantastic demonstration. Now, to describe all this quantum weirdness precisely, physicists need math. What are the main mathematical tools they use for polarization?
Yeah, we need precise language. There are primarily two formalisms, each with its strengths and weaknesses. First, there's Jones calculus. This uses these neat little 2x1 complex vectors called Jones vectors to represent the electric field amplitudes. And 2x2 complex matrices, Jones matrices, represent optical elements like polarizers or wave plates.
Complex numbers, so phase matters.
Exactly. Jones calculus is perfect for fully polarized, coherent light where the phase relationship between the components is critical. It's basically the same math as state vectors or outgets in quantum mechanics.
But it's a limitation.
It just can't handle unpolarized or partially polarized light. It assumes perfect polarization. For those more general cases, we use Stokes-Muller calculus. This uses 4x1 real vectors, Stokes vectors, which are defined in terms of intensities, things you can actually measure directly.
Real numbers, based on measurement.
Right. And 4x4 real matrices, Muller matrices, represent the optical elements. This framework is much more general. It can describe any state of polarization, fully polarized, partially polarized, or completely unpolarized.
So what's the trade-off?
It loses absolute phase information. Because it's based on intensities, you can't use it to model things like interference between two separate laser beams, where phase is crucial. But it does let you easily calculate the degree of polarization, or DOP. It's a number between 0, totally unpolarized, and 1, perfectly polarized, telling you exactly how polarized your light beam is.
Okay, Jones for pure states, Stokes-Muller for the real-world messiness. Got it.
Yeah.
Now, these are math tools. Is there a way to visualize all these possible polarization states together more intuitively than just equations?
Yes, and it's a really elegant tool. The Poincaré sphere.
A sphere.
A sphere. Imagine mapping all possible polarization states onto the surface of a sphere. It uses the three polarization-dependent Stokes parameters as, essentially, the x, y, and z coordinates of a point on the sphere's surface.
Okay, so where do different polarizations live on this sphere?
It's beautifully organized. The North Pole represents perfect right-hand circular polarization, RHC. The South Pole is left-hand circular, LHC.
Poles are circular. What about the equator?
The equator represents all possible linear polarizations. So horizontal would be one point on the equator, vertical would be directly opposite it, plus 45 degrees would be another point, negative for 45 degrees opposite that, and so on all around the equator.
And everything else, elliptical.
Exactly. All the other points on the surface of the sphere, between the equator and the poles, represent all the possible states of elliptical polarization. A really neat feature is that orthogonal states that a polarizer would completely distinguish, like H and V, or RHC and LHC, are always represented by points directly opposite each other on the sphere, antipodal points.
That's useful.
Very. And things like wave plates, which change polarization, correspond to simple rotations of the sphere. It turns complex polarization changes into intuitive geometry. It's a fantastic tool for visualizing and even designing optical systems.
Okay, this is where the physics meets the real world. We have the theory, the math, the visualization. How do we actually make and control polarized light in a lab or in technology?
Right, we need devices. We use specialized optical components that manipulate either the amplitude or the phase of the light's orthogonal polarization components.
Let's start with the basics.
Yeah.
Polarizers. How do they actually filter out the unwanted polarization?
Polarizers are the workhorses. They take unpolarized light and spit out polarized light by selectively transmitting one polarization state and blocking, or sometimes reflecting or absorbing, the one orthogonal to it. There are a few main ways they do this. Maybe the most common are dichroic polarizers, like the Polaroid sheets in sunglasses.
Dichroic, meaning two colors.
Sort of. It actually refers to selective absorption based on orientation. They use materials, often polymer films stretched with aligned molecules in iodine, that absorb light much more strongly if its electric field is aligned with the long molecules. So light polarized parallel to the molecular chains gets absorbed, while light polarized perpendicular to the chains gets transmitted. Interestingly, the transmission axis is perpendicular to the alignment direction.
Okay, so it's like tiny molecular blinds.
Yeah, that's a decent analogy. Then there are birefringent polarizers, like Nicol prisms or Glan-Thompson prisms. These use crystals, like calcite, that have different refractive indices for different polarizations. They exhibit double refraction. Unpolarized light entering the crystal gets split into two separate beams with orthogonal polarizations, the ordinary and extraordinary rays. The prism is cleverly designed to then get rid of one of those beams, often using total internal reflection, leaving just one purely polarized beam.
Clever. Any other types?
There are also reflective polarizers. One type is the wire grid polarizer. Imagine a grid of incredibly fine parallel metal wires. Light polarized parallel to the wires gets reflected, while light polarized perpendicular gets transmitted. These work well over broad wavelength ranges, especially in the infrared.
Like a tiny antenna grid.
Exactly. And another reflective type uses Brewster's angle. When light hits a surface like glass at a specific angle, Brewster's angle, the reflected light becomes perfectly polarized parallel to the surface. The other polarization is fully transmitted. You can make a polarizer by stacking plates at this angle.
We'll come back to Brewster's angle, I bet.
Oh, definitely. It's key to understanding glare.
Okay, so polarizers create polarized light. But what if we have polarized light and want to change it, say, from linear to circular, or just rotate the linear angle? That's where wave plates come in.
Exactly. Wave plates, or sometimes called retarders, are all about manipulating the phase difference between orthogonal polarization components, not blocking them like polarizers do. They also rely on birefringence, just like some polarizers. The material has different refractive indices along two perpendicular axes, the slow axis and the fast axis.
So light travels at different speeds depending on its polarization relative to these axes.
Precisely. One component travels slower than the other through the plate, which introduces a delay or a phase shift between them. The total phase shift or retardation depends on that difference in refractive indices, the thickness of the plate, and also the wavelength of the light.
Are there standard types?
The two most common are the quarter wave plate and the half wave plate. A quarter wave plate introduces a 90-degree or 2 radians phase shift. Its main trick is converting linear polarization into circular polarization, provided the input linear light is oriented at 45 degrees to the waveplate's axis. It also works in reverse, circular to linear.
Okay, quarter wave for linear to circular conversion. What about half wave?
A half-wave plate introduces a 180-degree, or peradians, phase shift. Its primary job is to rotate the plane of linear polarization. If you send in linearly polarized light at an angle, say, relative to the waveplate's fast axis, the output linear polarization will be rotated by an angle of 2.
Double the angle. Interesting.
Yeah, it effectively flips the polarization state across the fast axis on the Poincare sphere. Very useful for rotating polarization without using bulky prisms.
This isn't just lab stuff, though. Where do we see polarization happening naturally out in the world?
Oh, it's everywhere once you start looking. And what's really neat is that two of the most prominent examples, glare from surfaces and the blue sky, actually stem from the same fundamental physics. It's basically down to how tiny oscillating electric dipoles radiate light.
Okay, let's start with the familiar one. That really annoying glare off water or a wet road or even sometimes a window.
That's polarization by reflection, and the key concept here is Brewster's angle, which we mentioned earlier. When unpolarized sunlight hits a non-metallic surface like water or glass, the light that reflects off it becomes partially or sometimes even fully polarized. At one specific angle of incidence, called Brewster's angle, the reflected light is perfectly linearly polarized, and its electric field is vibrating parallel to the surface. We call that spolarization.
Is for surface.
That's a same correct, actually, German for perpendicular. Perpendicular to the plane of incidence, but parallel to the surface, yeah. The other polarization, polarization parallel to the plane of incidence, gets fully transmitted into the material at this angle. None is reflected.
Why does that happen at that specific angle?
It's quite elegant. At Brewster's angle, the angle between the reflected ray and the refracted ray, the one going into the water, is exactly 90 degrees. Now, think about the light trying to reflect. The incoming light makes electrons in the water oscillate. For polarized light, those electrons would be oscillating along the direction the reflected light needs to go. But an oscillating dipole doesn't radiate energy along its axis of oscillation.
Ah, so it can't reflect the polarization.
Exactly. So only the socularization reflects. The angle is given by Brewster's law. The tangent of Brewster's angle is the ratio of the refractive indices, N2, N1. For air to water, it's around 53 degrees.
And since glare from roads and lakes is usually reflected at roughly glancing angles near Brewster's angle.
That glare is strongly horizontally polarized, which is exactly why polarizing sunglasses with their vertical transmission axis work so well to block it. They block the horizontal glare.
Clever. Okay, what about the blue sky? You said that's polarized too.
Indeed. This is polarization by scattering, specifically Rayleigh scattering. Sunlight comes into the atmosphere and hits the air molecules, mostly nitrogen and oxygen. The light's electric field makes the electron clouds in these molecules oscillate.
Like tiny antennas.
Exactly. They become tiny oscillating dipoles that then re-radiate light in all directions. That's scattering. Now, Rayleigh scattering is much stronger for shorter wavelengths. It goes as 1 over lambda to the 4th power. That's why blue light gets scattered way more than red light, making the sky appear blue.
Right, the blue sky. But where does the polarization come in?
It comes from that same dipole radiation pattern again. A dipole doesn't radiate along its axis of oscillation. So imagine sunlight coming from, say, the horizon. The air molecules start oscillating horizontally. If you look straight up, perpendicular to the incoming sunlight and perpendicular to the oscillation direction, the light you see scattered down towards you cannot have its electric field oscillating along your line of sight. It ends up being predominantly linearly polarized, with its electric field horizontal perpendicular to the plane containing the sun, the air molecule, and you.
So the polarization depends on where you look relative to the sun.
Absolutely. The polarization is strongest when you look at the sky at a 90-degree angle away from the sun. You can actually see this effect with polarizing sunglasses. Rotate them while looking at the blue sky 90 degrees from the sun, and you'll see the sky dramatically darken and lighten.
Wow. Some insects use this, right?
They do.
Yeah.
Bees, for example, are thought to navigate using this pattern of polarization in the sky, even when the sun itself is obscured by clouds.
That's amazing. So glare and the blue sky, both explained by how tiny dipoles radiate light.
Fundamentally, yes. It's a beautiful connection between everyday phenomena and basic electromagnetism.
Okay, so from the everyday to the truly mind-bending. This same property Photon polarization was absolutely central to unlocking some of the deepest, weirdest aspects of quantum reality. Stuff that even baffled Einstein's spooky action at a distance.
You're talking about quantum entanglement. And yes, photon polarization was and still is one of the best ways to study it. Entanglement is when two or more particles become linked in such a way that they share the same fate, the same quantum state, no matter how far apart they are. You can't describe one without describing the other.
Like they're still connected by an invisible thread.
In a way, yeah. Polarization-entangled photon pairs are a classic example. They can be created in labs using a process called spontaneous parametric down conversion, SPDC. A special crystal takes one incoming high-energy photon and splits it into two lower-energy photons that are entangled in polarization. A common entangled state, one of the Bell states, might look like this. After nasa VA plus VA.
Okay, what does that mean in plain English?
It means photon A is horizontal and photon B is vertical. Or photon A is vertical and photon B is horizontal, simultaneously. They're in a superposition of these two possibilities. The crucial, spooky part is this. While their correlation is perfectly defined, if A is H, B must be V, and vice versa, the actual polarization of each individual photon, A or B, is completely undefined until you measure it.
Undefined until measured.
And the moment you measure photon A's polarization, say you find it's horizontal, you instantly know, and in fact, photon B instantly becomes vertical, regardless of whether B is in the same lab or across the galaxy.
That instantaneous connection, that's the spooky action.
That's what bothered Einstein so much. It seemed to violate the idea that influences can't travel faster than light, locality. He suspected quantum mechanics was incomplete, that there must be some hidden instructions, hidden variables telling the photons what to do in advance.
So this led to a huge debate. Is quantum mechanics the full story, or are there hidden variables Einstein suspected? How did Bell's theorem resolve this?
John Stuart Bell in the 1960s did something brilliant. He took this philosophical debate about hidden variables and locality and turned it into a concrete, experimentally testable prediction. He proved mathematically that any theory based on local realism, combining Einstein's assumptions of locality, no faster than light influence, and realism, properties exist before measurement, would put a strict limit on how strongly the measurements on entangled particles could be correlated. This limit is expressed as a Bell inequality. A famous version, the CHSH inequality, basically says a certain combination of correlation measurements, let's call it S, must be less than or equal to 2 if local realism holds true.
Okay, so local realism predicts correlations are capped at 2. What does quantum mechanics predict?
Quantum mechanics, because of entanglement, predicts stronger correlations. It predicts that for ideally entangled particles, you can actually measure a value of S up to 2.2, which is about 2.83. This value is sometimes called the Tsirelson bound.
So a clear difference. Quantum mechanics says correlations can be stronger than any local realistic theory allows.
Exactly. Bell turned it into a quantitative test. Measure the correlations. Does the result stay below 2, agreeing with Einstein's intuition? Or does it go higher, potentially up to 2.83, agreeing with quantum mechanics?
And what did the experiments show? Did reality follow common sense, or was quantum mechanics right about this spookiness?
The experiments, starting seriously with John Clauser and Stuart Friedman in 1972, and then famously refined by Elaine Aspect in the 1980s, and many others since with increasing precision, they have consistently, decisively found that nature violates Bell's inequality.
Violates it, so the correlations are stronger.
Yes. The measured correlations perfectly match the predictions of quantum mechanics, reaching values significantly greater than 2. These experiments have effectively ruled out the entire class of local hidden variable theories. They provide incredibly strong empirical evidence that our universe is fundamentally non-local, or perhaps not real in the way Einstein hoped. It doesn't conform to our classical intuitions. It's one of the most profound experimental results in the history of science.
Wow. So the universe really is that strange. And this quantum weirdness, revealed so clearly by photon polarization, isn't just theoretical musing anymore. It's being harnessed for powerful new technologies. Let's talk quantum computing.
Absolutely. Photon polarization turns out to be an excellent way to physically realize a quantum bit, or qubit. Photons have huge advantages. They travel at the speed of light, they don't interact much with their environment, so they maintain their quantum state well. They're ideal flying qubits for transmitting quantum information.
So how do you encode information?
The simplest way is just to assign orthogonal states to 0 and 1. For example, Horizontal polarization Gordo could be your qubit state Sinya, and vertical polarization Oreo could be 1Z. The real power comes from superposition. A single photon can be in a state like 1Z plus 0, representing both 0 and 1 simultaneously. This allows quantum computers to explore many possibilities at once. That's the idea behind quantum parallelism. Any point on the Poincare sphere is a valid qubit state.
And how are people actually building these?
A major push right now is in integrated photonics. Researchers are essentially building miniature optical circuits on silicon chips, tiny waveguides, beam splitters, phase shifters, detectors, all designed to generate, manipulate, and measure these photonic qubits at scale. One promising approach is measurement-based quantum computing, which uses highly entangled states called cluster states as a resource. Photons are particularly well suited for creating these.
Okay, quantum computing. What about secure communication? How does photon polarization enable quantum key distribution, QKD?
QKD is a way for two parties, let's call them Alice and Bob, to generate a shared, secret random key for encryption, where the security is guaranteed by the laws of quantum mechanics, not just by assuming an eavesdropper has limited computing power. The most famous protocol is BB84, and it directly uses single photon polarization. Here's the gist. Alice sends Bob a stream of single photons. For each photon, she randomly encodes a bit, 0 or 1, using one of two randomly chosen polarization bases. Either the rectilinear basis plus H or V, or the diagonal basis, x plus 45 degrees or negative 45 degrees.
Lots of randomness.
Key to security. Now, Bob receives the photons. For each one, he also randomly chooses to measure it in either the plus basis or the x basis. He has no idea which basis Alice used for any given photon.
So sometimes they'll guess the right basis, sometimes the wrong one.
Exactly. After they've exchanged all the photons, they communicate over a public channel like a normal phone line, but they only compare the bases they used for each photon, not the measurement results. They keep the results only for the photons where they happen to choose the same basis. If they use the same basis, Bob's measurement result should perfectly match the bit Alice sent. These matching results form their shared secret key.
Okay, but where does the security come in? What if someone, Ease, tries to listen in?
That's the quantum magic. If Eve tries to intercept a photon, say one Alice sent in the plus basis, Eve doesn't know if Alice used plus or x. If Eve guesses wrong and measures in the x basis, she forces the photon to collapse into a diagonal state.
She changes it.
She irreversibly changes it. When Bob later measures that photon, even if he correctly uses the plus basis, there's now a chance he'll get the wrong result compared to what Alice sent. So after the basis comparison, Alice and Bob sacrifice a small part of their potential key bits and compare the actual values publicly. If they find more errors than expected from noise, they know someone was listening, and they discard the key and start over. Eve can't gain information without introducing detectable errors.
Because measuring disturbs the system. That's clever.
It's fundamentally secure based on physics. And photon polarization is great for this, especially for free space QKD sending keys between buildings or even up to satellites.
Amazing. Okay, moving beyond the really cutting-edge quantum stuff, polarization is already deeply embedded in technology we use every day and in scientific tools. How is it fundamental to something like a liquid crystal display, LCD?
LCDs are basically sophisticated light valves, and their entire operation depends on controlling polarized light. Think of it like a sandwich. At the back, you have a backlight producing unpolarized light. Layer 1, a rear polarizing filter. Let's say it polarizes the light vertically. Layer 2, the liquid crystal layer itself, placed between transparent electrodes. Liquid crystals are weird materials. Their molecules can be aligned by electric fields. In the off state, no voltage, the molecules are typically arranged in a twist, maybe a 90-degree twist.
Twisting light.
Exactly. As the vertically polarized light passes through this twisted liquid crystal layer, its polarization plane gets rotated, following the twist, so it might emerge horizontally polarized. Layer 3, a front polarizing filter oriented orthogonally to the rear one. So if the rear was vertical, this one is horizontal. So in the pixel's off state, vertical light enters, gets rotated 90 degrees by the liquid crystal, becomes horizontal light, passes straight through the horizontal front filter. The pixel appears bright.
Okay, bright went off. How does it turn dark?
You apply a voltage across the electrodes for that pixel. The electric field makes the liquid crystal molecules untwist and align themselves with the field, typically perpendicular to the screen. Now, the vertically polarized light from the back passes through the untwisted liquid crystal without its polarization being rotated. It arrives at the front horizontal polarizer, still vertically polarized.
And a vertical light hits a horizontal filter.
Blocked. The pixel appears dark. By carefully controlling the voltage applied to each tiny pixel, you control how much the polarization gets rotated and therefore how much light gets through the front filter. That's how you create grayscale and, with color filters, the full color images on your screen.
Incredible. All based on twisting polarized light. What about 3D movies and those ubiquitous sunglasses?
Polarization is absolutely key for both. Plays two images on the screen simultaneously, one for your left eye and one for your right. Each image is encoded with a different type of polarization. Typically, they use opposite circular polarizations, one right-handed, one left-handed. Your 3D glasses have filters that match this. The left lens only lets through, say, the left circularly polarized light and blocks the right. The right lens does the opposite, so each eye sees only the image intended for it, and your brain combines them to perceive depth.
Simple but effective. And sunglasses. We touched on this with Brewster's angle.
Yep. Polarized sunglasses are designed specifically to combat glare reflecting off horizontal surfaces, roads, water, snow, car hoods. As we discussed, this glare is strongly horizontally polarized. The lenses in polarized sunglasses are dichroic filters oriented with their transmission axis vertical, so they let vertically polarized light through, which is most normal ambient light, but strongly block the horizontally polarized glare. Makes a huge difference for comfort and safety, especially when driving or out on the water.
For photographers, a polarizing filter for their camera lens is often considered essential. What magic does it perform for them?
Oh, it's incredibly useful, partly because its main effects are very hard, if not impossible, to replicate convincingly with software later. First, managing reflections, just like sunglasses, but you can rotate the filter on the lens. This allows a photographer to minimize or even completely eliminate reflections from non-metallic surfaces, like window glass or the surface of water. You can suddenly see through the reflections.
Seeing through water.
Yes. Second, enhancing skies and reducing haze. Remember, the sky is polarized. By rotating the filter, the photographer can selectively block some of that polarized skylight. This makes the blue part of the sky appear much deeper and darker, increases the contrast with white clouds, and helps cut through atmospheric haze, making distant landscapes clearer.
More dramatic landscapes.
Definitely. And third, increasing color saturation. By removing the subtle or not so subtle reflective glare from the surface of objects, like wet leaves or the paint on a car, the filter allows the object's true, richer colors to come through. It makes colors pop.
Very versatile tool. Finally, let's look outwards. In astronomy, how does measuring the polarization of light from distant objects help us understand the universe? It seems like a very specialized measurement.
It is specialized, but polarimetry, the measurement of polarization, provides unique information that complements other astronomical techniques like measuring brightness, photometry, or chemical composition, spectroscopy. It often reveals physical conditions or geometries that are otherwise hidden. One major application is mapping cosmic magnetic fields. Certain processes, like synchrotron radiation emitted when superfast electrons spiral around magnetic field lines, produce strongly polarized light. By measuring the orientation of this polarization from things like jets coming from black holes or supernova remnants, astronomers can map the structure of the magnetic fields in those extreme environments.
Using light to see invisible magnetic fields. Cool.
Very cool. It also helps us probe cosmic dust and planet formation. Starlight traveling through clouds of interstellar dust gets scattered by the tiny dust grains, and this scattered light becomes partially polarized. The amount and wavelength dependence of this polarization tells us about the properties of the dust grains, their size, shape, maybe even their composition. This is crucial for understanding the stuff between stars and the environments where planets form in protoplanetary disks.
Learning about dust from polarized starlight.
Exactly. Polarization can also signal asymmetry in explosive events. For example, measuring polarization from supernovae has shown that the explosions are often not perfectly spherical, which gives vital clues about the explosion mechanism itself.
And looking way back to the early universe.
That's one of the most exciting frontiers. Scientists are meticulously searching for a specific faint swirling pattern called B-mode polarization in the cosmic microwave background, CMB, the leftover heat from the Big Bang. This B-mode pattern is predicted to be a unique signature of primordial gravitational waves generated during cosmic inflation, a hypothetical period of incredibly rapid expansion just fractions of a second after the Big Bang. Detecting it would be monumental, a direct window into the physics of the very, very early universe.
Wow, from sunglasses to the Big Bang's afterglow. This whole journey, from a basic property of light waves to quantum entanglement in cosmology, it's truly remarkable. What's next? What's on the horizon for photon polarization research?
Oh, the field is incredibly active. There's huge effort going into novel materials and device architectures. Things like nanophotonic devices, metamaterials engineered to control light in unprecedented ways, and especially those scalable integrated photonic circuits on silicon chips for quantum computing. Getting these complex quantum experiments off the optical table and onto a chip is key.
Taking quantum optics miniature.
Exactly. There's also interesting work at the intersection with high-energy physics and even fusion energy. People are exploring using the topological properties of certain polarized light beams to create robust beams for heating plasma in fusion reactors, or developing highly energetic polarized gamma-ray beams to probe the structure of atomic nuclei and test fundamental physics. And of course, advanced quantum communication and the quantum internet, pushing for faster, more robust QKD, and developing the components needed for a future global network that can distribute entanglement between quantum computers. Imagine distributed quantum sensing or computing clusters linked by flying photonic qubits.
A quantum internet. That sounds like science fiction.
It's a long-term vision, but people are building the foundational elements now. A related critical area is spin-photon interfacing. That's about efficiently transferring quantum information between stationary qubits, like the spin of an electron trapped in a material, and flying photonic qubits used for communication. Making that connection stronger and more reliable is essential for building scalable quantum networks and linking different quantum technologies together.
So, pulling it all together, what does this journey of understanding photon polarization really mean for us? Why should we care about the orientation of light waves?
Well, I think the story of photon polarization is just a fantastic example of how fundamental scientific curiosity can lead to the most unexpected and world-changing discoveries and technologies. It starts with simple observations about light and crystals, explains everyday things like the blue sky and why your sunglasses work. Then it forces us to confront the deep weirdness of quantum mechanics, like entanglement, completely changing our view of reality. And then that same weirdness becomes the foundation for potentially revolutionary technologies like quantum computing and secure communication. It shows how pursuing fundamental knowledge, even about something seemingly simple like which way light waves wiggle, can profoundly reshape our understanding of the universe and ultimately our technological capabilities.
That's a great perspective. What stands out to you the most from our deep dive today? For me, it might be that three-polarizer trick. It just seems so impossible classically. The next time you put on polarized sunglasses or look at your phone screen or even just glance up at a deep blue sky, maybe take a second to consider this incredible journey of photon polarization from a classical wave property through the quantum revolution, revealing a universe that's honestly far stranger and maybe more interesting than we ever imagined. We hope this deep dive has given you a useful shortcut to being well-informed on photon polarization and maybe sparked your curiosity to learn even more. Until next time, keep diving deep.